Hello everyone, we are Group 20. We're here to present the music recommendation system with LM-based chatbot. Our goal is to develop an emotional intelligent music recommendation system with a real-time chatbot that provides personalized and contextual relevant song suggestions based on user preference and emotional states. And we will utilize the diverse data and TraceV 3.5 tube and distribute root beta and apply the auto coder and contract learning to handle the real cases. For related work, compared to movie recommendation system with chatbot, its strength is it can use collaborative filtering cluster and tools for personalized suggestions and real-time interactives. But limitations is the struggle with code style issues, not emotional adaptability. So in our system, we will use the dynamic emotional intelligence and use enhanced personalization. So our system will go beyond the traditional movie chatbot. Compared to constructive learning of SMCRR, the strength is can self-supervised learning by construct positive and negative pairs to learn robust representations and effective in constructive domains. But challenge for the music recommendations, it's a struggle with high dimensional sparse music data and emotional contextual complexities. So compared to other GitHub projects like Chatbot music recognition system, it lack of personalized and struggle nuanced the user input. For the chatbot using AWS Next and MusicMe chatbot, they all lack emotional based recommendations. So in our system, we will use the emo raw beta GP 3.4 turbo and enhanced rating scale for deployment. Altogether will help us bridge gaps in pair work.
So for the dataset acquisition, we use these two datasets, Plus.fm and Spotify API dataset. So for Spotify dataset, we extract about 500K unique tracks with 10 plus quantitative audio features of each song. And here's the volume, velocity, and variety of this dataset. And for the data cleaning and pre-processing, we've done some filtering by relevance. That is, we discard those unnecessary features of the songs. And we also did the normalization for a standardization, uh, the quantitative data into the same scale. And for last.fm dataset, this dataset contains the songs with their song name, artist name, and the corresponding tags, which is defined by people. And the tags contain like rock, blue, jazz, these things. So we found out that the total number of all these tags is about 500K, which is a which is pretty large if we would like to make some analysis and make the recommendation based on this. So we plot the label frequency cumulative distribution against its cumulative frequency ratio. And then we use the 85% line as a threshold to cut it. That is, we keep the first 85% of the total number of the tags. And we found in this way we managed to reduce the number of tags into about 50K without losing its statistical power because the threshold is 85%. And finally, we made a data merge with these two data sets, and we merged them by song title and the artist name. So finally, our data set contains about 50K rows representing the numbers of unique records and 18 columns that refers to the basic information on and audio features and genre, which is the tag of these data sets. And here's an overview of our system. So firstly, the chatbot will initialize the conversation, and then we're going to have three conversations with the users, and then we try to analyze the emotion of the users, and we ask for the user's favorite song. So after the input of the user. We're gonna decide if we use emotion with favorite song or emotion artist song name only to make the recommendations. And I'll give you a live demo later. And so for the chatbot implementation, because we do need to engage the casual conversation with the user, so we do need the NLP. We use the GPT 3.5 for that. And for the emotion analysis, we use a model called Distill Roberta in Hugging Face. And this model will classify the user's emotion into these 7 categories for us to make the recommendation later. And for the web page implementation, backend, we built everything with Flask for API routing and processing. Front end, for the interface design, we use HTML, CSS, and for the user interaction, we use the JavaScript. And here's a picture of our whole file system. The app.py and recommendation.py refers to the implementation of the chatbot logic and the recommendation logic. And then we push it to the cloud to deploy the website, and we push the code base into a GitHub repository for some of the integration with render after. So now let me give you a live demo, and this is how our web pages look like. So firstly, the chatbot will initialize the conversation by explaining how it works and then ask, how are you doing today? So let's say I am good. It's great to hear. Says with whom you're feeling today. So let's say I'm very good. Is there a specific genre or artist you're in the mood for? Maybe I will like some pop music. So after these 3 conversations, it is going to ask me, and firstly going to analyze my mood, and then it's going to ask me to provide the song name by artist name, or I can provide only song name, artist name. And also I can choose to give him nothing. So it will make the recommendation based only on the mood. So let's say we choose one. Song name by artist name. I'll say no by Linkin Park, please. So the system takes a while if I choose one because this time the system takes 3 factors into account, which is my emotion, my favorite song, and my favorite artist. And the system is kind of complicated when all these 3 factors are input into the system. So it will take a while. Oh, here is the list. And if we click on the link, we will see the corresponding Spotify webpage here. Okay, and let me refresh and give you another example. Let's say I am feeling bad this time. Music can often help improve a specific type of music or artist. I want some blue music because I'm in a bad feeling. So it has some recommendation and said give it a try. I'll say, okay, thank you. So all these are casual conversations between the chatbot and the user. So this time I'm in a bad feeling. I don't have any songs in my mind right now, so I choose 4. And this time the list will be pop out pretty quick because it only used the emotion for the analysis. And here's the web page. Okay.
Okay, thanks, Pampai. Our recommendation system leverages emotion analysis and item-based careerability filtering to provide personalized music recommendation. It begins with analyzing users' conversations through Roberta, a advanced emotion detection model that categorizes emotions into predefined texts such as joy, sadness, or anger. These emotional insights act as a foundation for filtering songs that align with the user's mood. If the user provides preference, such as a favorite song or artist, a large language model interprets and integrates input into the process. For a user without specific preference, the system defaults to emotion-based filtering, addressing the co-star problem while ensuring privacy. Once the user's emotion or preference are identified, the system employs emotion filtering to narrow down the recommendation pool. Using text extracted from the last FM metadata, songs are filtered based on their alignments with the user's emotion state. This ensures that recommendation resonate with the user's current mood. However, last FM metadata pose challenges. Text or user-generated, noisy and highly unstructured, with over 50,000 unique texts. Clustering methods like K-mean or STP scan exploded to organize this data but proved ineffective due to its heterogeneity. Ultimately, we relied on large language models such as GPT 3.5 Turbo to semantically interpret and extract emotional and general information directly from the text, producing clean and actionable results. With emotion filtering providing a narrow pool of relevant songs, we then applied item-based narrative model to identify tracks most similar to the user's preference of emotion-aligned songs. Using Spotify quantitative audio feature data, normalized attributes like danceability, energy, and tempo, we experimented with multiple methods to achieve accurate similarity-based recommendation. Our first approach was K-mean clustering, which groups songs based on feature similarity, while clustering acoustically similar tracks was effective to an extent. K-mean struggled to handle heterogeneous data and lacked the granularity needed for personalized recommendation. Moreover, it provides no mechanism for ranking or scoring items, making it suboptimal for this task. It will improve we implement Synchro, a constructive learning framework. Synchro generates positive and negative pairs to train a neural network encoder, optimizing representations to maximize the similarity within pairs and minimize it across unrelated samples. While Synchro demonstrates its ability to learn robust embedding, it faces key challenges. The rules decrease slowly, likely due to the limited diversity in song features compared to the data size. Our most successful approach was autoencoder with similarity rules, which compress the song features into low-dimensional embedding while capturing nonlinear relationships. The autoencoder architecture featuring into two encoding layers and decoding layers. It coverage faster than Synchro and achieved lower loss values, enabling efficient training. Songs with similar audio characteristics were closely grouped into the latent space, enabling precise similarity-based ranking. Despite having only 150 labeled similar song pairs from the last FM, the autoencoder demonstrates strong performance on unlabeled data, showcasing its ability to generalize effectively. This makes it an optimal choice for our project. Okay, thank you for listening.